Today we're talking about communicating with your meters. Today we're going to cover not just wireless communications for AMI, but for local communications, and I'm also going to touch on a little bit on PLC communications. So we're going to touch on a little bit of all of those. I'm going to try to relate each one of those types of communications to metering, to their usage, and some bits about how they relate to testing each one of those communications, and maybe some of the things that you can run into in the field to make those communications better, and a couple of different ways that TESCO can help out in those areas. So first, a little bit about why do we need to communicate to meters? Well, for most of us, that's kind of obvious, but prior to the age of the electronic meters and AMI and AMR, electromechanical meters, of course, served only one real purpose, and that was to measure the energy and display it on the dials on the front of the meter. So in order to get that information from the meter, there had to be a person that actually had to go out and record those readings, write them down in a notepad, and then bring it back. And then there was a comparison from this meter read to the last meter read, and then you knew your consumption. Of course, nowadays we have electronic meters, which are capable of a lot more than just reading the usage over a period of time. A lot of instantaneous information can be retrieved from these meters, but in order to do that, obviously there has to be a way to easily communicate to each one of these meters. So again, two main reasons to communicate to the electronic meters. One, to locally check the settings, firmware revision, operation of the meter, and the communications module, the AMI communication module that may be in that meter. And then, of course, more importantly, for billing purposes, load management, service, the remote communications is of critical importance to each utility. So communications can also be used to update the firmware in the meter, disconnect residential service for non-payment, emergency situations, pulling the meters and so forth. Also, local communication can be used to do those same software updates and test that disconnect function. So when we go through this presentation, you'll see I'll draw some parallels between the local communication and the remote communications, keeping in mind here that if ever there's a meter that fails to be able to do the remote communication, that local communication should be available to you. So starting with the local communications, obviously most local communications are done through the optical port on the meter. This optical port transfers the electronic information that's inside the meter to an IR light source, and then transmits that outside of the meter for external pickup. It's also bidirectional. It's a serial interface that receives IR light as an input and then converts that back into electrical signals that can be read by the meter electronics. This picture on this slide is taken from ANSI C1210. It basically defines a couple of things. First, there's two infrared light conduit ports. You see the two circles in the middle. The leftmost one is the transmitter from the meter to the pickup, and then the right one is for receiving information. Also defined in this drawing is the mechanical feature that is required to be around those two infrared light conduits. Some meters have them. It is part of an ANSI C12 spec, but some don't, as you saw if you were watching some of the videos before our presentation started. Some of them just have on the plastic, it's just flat, and they could be somewhat problematic to get a hold of. The purpose of the mechanical feature here is obviously to line up the transmit and receive ports to the probe or the pickup that you place on top of there. So on the other side of the meter, of course, is the optical port readers. There are two terms that are commonly used for two different purposes, right? The first is a pickup. Typically we refer to a pickup as the optical port receiver that is used to just pick up the metering pulse output, right? For those of us in the test industry, we know that pulse well. That's the pulse that is required by all test boards in order to get from the meter what the how much energy is being consumed by the meter, and that's the signal that tells us how to compare the consumption by the meter to the consumption by the reference standard, and then that comparison defines the accuracy of the meter. It's a very critical output that comes from the meter, and the pickup that we have is called our 1037. You see a picture of it there, both on the meter and kind of laying on the table. We've been using that device for quite some time. And we have a couple of different flavors of that to go to a couple of different test boards that we manufacture. The other type of optical port reader is typically described as a probe. Okay, so the probe differs from the pickup in that it is, number one, it is bidirectional, right? So it's going to receive the IR light information and convert that to an electrical signal, which is interpreted by a computer. And then it also takes an electrical signal from a computer and converts that back into IR light and for interpretation by the meter. So now you can send commands to the meter and retrieve information with a fairly complex protocol, also part of an ANSI spec. So here you see we have our 1038 here. Most of the modern probes communicate via USB back to a computer. Our device does the same. In this case, in the older versions, we actually had the old DB9 RS-232 to do the serial communications, but as we all know, those connectors and that protocol has kind of gone by the wayside in lieu of USB. So USB back to the computer. Your computer will be running the meter manufacturer software typically, where you're going to use that software to query the meter, find out its status, check registers, firmware revisions, all those other things that we talked about earlier, and also to send commands to the meter to for the residential meters to open and close the service disconnect switch. A third type is kind of a advancement from the original probe, the wired USB probe, and that's a wireless probe, right? These are becoming a little bit more popular because if you do have to use the local communication to the meter when you're out in the field, and it's inclement weather, raining, snowing, etc., it's fairly difficult to get your laptop out to the site, keep it from getting wet or damaged in any way. And for a wireless probe, depending on the type of communication, some are Bluetooth, some of are wireless. Our CAT 1039WP happens to be wireless and has a pretty long distance for transmission. You can go back to your truck, open up your laptop there and communicate to the meter outside or inside, away from the weather. These devices are also good in lab environments. Actually, if you've got a big test board or a multi-position qualification board, for instance, and you want to easily communicate to a bunch of those meters, checking all their settings and firmware revisions, etc. Having a wireless probe is kind of easy, because you could just kind of walk up to the front of the panel and move it from one to the other, and then walk back to your laptop, which may be in a different location, or you don't want wires hanging in front where people can trip over them. It's kind of an easy way to communicate to the meters there without the messiness of the wiring laying around. Pardon. Finally, there's a device now that we manufacture called a 1035, which actually is a combination of those two pickup devices, right? So you have the same pickup head can be mounted to the meter and do both the optical pickup for the meter testing, as well as the bidirectional communication through the USB, so that you can talk to the meter. This particular device is really helpful when you're doing kind of your complex functional testing, functional and accuracy testing of your meters before you deploy them out in the field. So if your utility requires that you do both functional checks and accuracy checks before the meters go out, you might want to get a test board, okay, and power up the meters just with the voltage, and have a device like this combination device in here, where the pickup signal would be fed back into the test board to do your accuracy testing. And then the USB cable can be brought back to a computer, so that the computer can do the functional checks with the disconnect, with the checking of all the firmware revisions, etc. The types of things that are checked prior to deployment for all your meters. So you have one device there that connects to the front of the meter. Typically, if you were doing this kind of testing before, where you would be doing accuracy testing and the serial communications, you would have to switch those heads, right? You'd have a separate dedicated pickup head, you'd have a separate dedicated probe, and you'd have to keep switching those. If you could picture this, you could also have, if you've got a multi-position test board, you could get a bunch of these things and then just plug them in all to each one of the sockets, and really never have to get up other than changing the meters. So as we mentioned here in the lab, you're doing your communications to do the functional testing on the meters. You're using the pickup pulses for accuracy testing, and then the combo pickup head can be used to do both at the same time. And it's a really valuable tool to have to save time and money as you're doing your checkouts before deployment.
Hey, John.
Yeah.
We do have a question coming in here. Do you have any learnings you might be able to share specifically relating to the remote disconnect process? I guess, I'm trying to read this. Have you created anything to help manage this potentially, I'm going to say this wrong, litigious progress?
Litigious, maybe. Yeah, there you go.
This is way above my knowledge, so I'll let you handle it.
Actually, TESCO's been working with meter manufacturers for quite some time on disconnect testing, both in the lab and in the field. There are a number of things that we've had to work into both our boards and some of the devices that we created. Actually, go back here. So one of the devices that we've released over the past year or so is this catalog 1039. Now I listed this particular product under the wireless probe function in my description here, but this device actually can be used on its own. So you can program, let's say, a password into the meter, or sorry, into the 1039 device, and then that device has a battery in it. You can charge it up from a laptop, your desk, whatever, and then take that device out into the field. And you can see on the left-hand image here, there's three buttons across the top. One, the middle button turns the device on because there's like a battery saver mode in there, so you don't want the battery running out while you're doing your runs. But you can go right up to your meters once the password's programmed in the device. There's an application that comes with the device as well, and then you press the open button, and you can, without using a laptop or a probe or any other device like that, you can actually go in and open up the disconnect or close the disconnect. Particularly useful, I guess, in the field, especially for anybody that's actually gone out on these kinds of calls. Doing a service disconnect for non-payment. You want to be in, you want to be out. You don't want to be stumbling around with laptops and cables and communications and software and things like that. This device will you just walk up to the meter, hit the button, it opens a disconnect, you hop back in your truck, and away you go. That device also can be used, again, as I mentioned, in the lab. Both we talked about the wireless communications to the meters, but you could use that in the lab as well if you're testing disconnect function and you're not really doing a whole functional test with checking serial numbers and firmware revisions and things like that. If you're just checking the disconnect functionality, it's a real easy device to use. If you've got, again, a multi-position qualification board, you can take that 1039 and just go from one meter to the next, hitting the open button, and click, 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 they all open up, and you go click, click, click back through, and they're all closed, right? And of course, you want to do a double check before you deploy those meters to make sure that they're closed before you deploy them. Hopefully that answers the question there.
I got it. Yes, thank you.
Okay, great. Thanks. So, like I said, in the field, we do that serial communication to do meter readings. Again, we're going to go into some of the other types of remote communications in a little bit. But here we want to, if those meters can't be read by the radio system for whatever reason, you want to be able to go in and get that meter reading one way or another, right? That's one thing that we're trying to avoid, but that's one thing that local communications are important for. Things to consider when testing or using your optical port if you're having problems. You want to check, first of all, if you're looking into buying or getting some probes. You want to look at whether you want to do a hardwired USB or wireless connection, depending if you're using it in the lab or out in the field. That may be important to you. Some of the features that I talked about on the mechanical side of things on the face of the meter, they also used to come with a metal face on them. So all the pickups and probes that are manufactured today have little magnets in them, so they'll stick to the front of the meter and automatically align the IR ports. But as most of us know, a lot of those metal facings have been removed from a good deal of the meters, and we just have a plastic mechanical feature there. You might want to look at getting a little device like we have pictured down here. I think that's a 1041, Andy. So that device is
that is correct.
Yeah, it's a pressure fit into the plastic, and then so that'll stick on there real good as a pressure fit. It won't fall off. And then on the front of it has the metal. and then you connect your pickup or your probe to that with the magnets. Also, things that may run into problems in the field when you're using optical pickups is ambient light intrusion, right? So if it's a really sunny day, some pickups have problems with that because that ambient light that comes through those plastic or glass features are going to disrupt that IR signal coming from the meter. And then, of course, as we all know, on some of the older meters, you have damage, scratching, fogging, plastic meter covers could interrupt that signal. One of the remote communications types that we're going to talk about today briefly here is power line carrier, also called PLC. This mode of communication actually transmits the serial information to and from the meter through the power lines, right? So what you're using here, and you see this actually, there's a lot of this type of equipment for homes nowadays, right? So you have a lot of the smart things in your house can talk along the power lines within the house. This is obviously a much more industrial and robust methodology to talk to the meters. It's really good in that the existing, obviously the power cables are all in there and they're all going to the customer sites. So fitting up the communications equipment to those power lines saves you some money in the deployment. The basic technology for this is, as you would imagine, you're just taking a high frequency serial signal and riding it on top of the 60 hertz power signal. Typically, this is done around the zero crossing point, and the technology has been used in a lot of different places. It's usually used where you have a fairly sparsely set up region where you have a number of meters that are not really close to one another, that can't, share a radio antenna or repeater or concentrator, or even we've seen them where there's you have meters with dual communication protocols built into them, where they might have a PLC card in there and a radio. And then depending on where the meter is put, you could use one or both of those communication pathways to get to that meter. The benefits of this, as I mentioned before, it's a bidirectional protocol, so you can talk to the meter, you can open and close service disconnects, you can get all your meter readings, you can get anything that are in the meter tables back to a head-end system. And again, the technology here using the existing wiring is always an added benefit. From a testing company standpoint, PLC testing in our equipment is kind of difficult, where the PLC testing in a lab, for instance, for utilities, where the meters, they want the meters to be able to they want to be able to plug the test board into the wall and then just use existing technology, whether it be a kind of remote test device for the PLC that they can just plug into an outlet and talk to the meter, or even using the infrastructure that they already have built in, from whether it be a substation or whatever, where they're going to actually send a signal to that and say, okay, talk to this meter, give it an address, and pick up that information. Extra wires and things like that are trying to, the utilities that we've been dealing with lately, the meter shops are trying to get away from like special wiring and things like that. So so the testing that PLC using the standard MQB and test board technology requires that the test board not only do the job that it was intended for, but also be able to pass that PLC signal through the board into the meter and back, right? So one of the challenges to that are typical modern test boards don't really have a direct connection between the power cord on the test board and the meter socket itself. Typically what happens there is the power cord is just going into to power some say DC supplies, and then those DC supplies power electronics, and the electronics then generate the phantom voltage and current used for the meter testing. So PLC through that line cord is somewhat difficult because of that separation. Another challenge in our testing and working with PLC signals is it is I say here nearly impossible, but it's somewhat difficult to get that PLC signal through an isolation transformer, right? So as you could imagine, as I mentioned before, the power cord coming into the system usually doesn't even go directly to the socket. Obviously, it's either going to go through a transformer or it's going to go through a bunch of DC supplies and so forth. So there's a great disconnect there. So what you need in order to test this through that power cord is a way to it's a different mode whereby you connect the power line straight through into the meter socket. Now, normally you would do this through a step up or isolation transformer, because you're just usually getting single phase 120 volts out of your wall socket. And if you're testing a 240 volt meter, you need to step that voltage up. Well, in this case, you can't use the isolation transformer for the reason I said before. So here you have to do something like an auto transformer, where you have a common line between input and output, so you can pass that signal from one side to the other without breaking that signal up. The other,
John?
yeah.
Sorry to interrupt.
That's okay.
I think you may have answered this, but I just want to double check. It came in and I just saw it pop up here. How can I test PLC communications in the shop?
So yeah, as I was talking about there, some of these challenges are just experiences that we had in trying to test this type of communication in lab setups, right? But all of our equipment now is capable of doing this testing by putting the test board or the MQB or whatever into a PLC test mode, where we're not our typical digital power source for the phantom load and voltage is removed from the meter socket connections, and then we just connect a multi-tapped auto transformer to vary the voltage just from different nominal voltages to whatever the meter needs, but also allowing that pass-through signal right from the power cord. So what you would do in the lab, as I mentioned before, I'll use TWAX as an example, where we've worked mostly with the Acquire folks on TWAX signaling. There they have a device called a PRTU, which is basically a little case. You open it up and it's got all the electronics in it. And then you can take that device and plug that directly into a wall socket, where you have maybe a shared circuit with the test board that you're using, and then you have a computer connection to that PRTU and a set of software, and you can command that device to send and receive signals to and from the meter. And then with the TESCO board in PLC test mode, that signal will pass right through the line cord. That's good there. The other challenge that we face is that sometimes PLC signals can draw upwards of 50 amps of current when they're doing communications. Just because of the nature of the way the signal is transmitted, you can get that burst of high current, whether it be through the command, the whole command, or at the beginning or end of the command. We can see those spikes. One of the things that we had to do was come up with unique and interesting ways to protect our equipment from blowing circuit breakers, etc., when that 50 amps comes through. But also we had to make sure that we're adequately protecting our board during normal circumstances, right? So you can't just throw a 50 amp breaker on there and call it a day. You have to just have kind of redundant protection devices in parallel for the two different modes. So, the next form, probably the most popular form of remote communications to meters, is a wireless network kind of communication, typically referred to in the industry as a radio. Talks at radio frequencies. Each one of the meters that participate in this type of communication will have a radio board, made by the manufacturer of the meter, or just communication manufacturers might supply that board to the meter. And then you have, again, that bidirectional communication to and from the meter over the airways, and then various components in between, depending on the topology of the network and the type of signals that you're using. That signal will get all the way back to a head-end system where you can collect all that information. As I mentioned, this is obviously the most broadly used type of communication to the meters, and has been able to advanced network and grid technology quite a bit over the past few years, being able to do things not only just reading meter information back into the head end for billing, but also for service, outage checks, load profiling, all different kinds of things that help secure and make more robust our network and our grid. So I talk here. I'm watching my time too, Andy. So there's two main types of radio networking. Again, I'll preface this with I'm not a network expert, but I do know what we've had to do to help service our customers in their AMI deployments and some of the problems that they run into. And we've made obviously some equipment, some test boards, and some other devices that have helped the implementation of these networks. So the two basic types of networking topologies that are used today are one was called point to multipoint, and the other one is a mesh network. As far as my research is concerned, it seems like the mesh networking is probably the more commonly used. The P2MP topology is typically, as it sounds, you have a main signal that goes out maybe on a fiber. It goes out to a central antenna or an array of antennas, and then broadcasts out to all the meters in its in its area. That is a great topology to use for typically more densely populated areas where there's a lot of meters in a certain area. You have one antenna that can reach, a few hundred or even thousand meters at a time. The drawback to that topology, of course, is if you have that single point concentrator going back to the head end, that's a single point failure, right? So if that antenna or antenna array fails, and of course there's always redundancies built into these systems, I'm not going to knock them, but that is always the knock on the P2MP type of topology. Of course, in the mesh networking, that protocol is a little bit different, and it prides itself on its ability to remain up even when problems occur, right? So in mesh networking, the communication is from meter to meter, and then meter to collector, and then collector to back to the head end through some other components. And of course, there's there's other components, repeaters and stuff that help with redundancies and fault tolerance type things. But the mesh network is built so that there's there's a whole logic to the communication from like any given meter back to where that signal has to go, where there's multiple pathways defined. When a meter joins a mesh, it could take a long time for it to join initially, just to figure out all those different pathways and figuring out the best way to get back. That's the most solid connection. But there's also a case where, so if if it's communicating, if a given meter is communicating to another meter in the next block, and then another meter in the next block back to a a collector, and one of those goes down, the mesh will repair itself. So instead of talking to the meter next door, maybe it hops over to the meter 2 doors away and then rebuilds that communication pathway. The P2MP topology is a little bit less susceptible to RF noise because they use licensed frequency bands. So they're the only ones residing in a certain frequency band, so nobody else can kind of interfere with that signaling. In mesh networking, they use unlicensed frequency bands, which means that there are other components that may come up in that area that may be talking in that same frequency band, right? So that could cause interference, that could cause time delays and lags in getting information for particular meters. As we talked about, the benefits to this type of communication, radio communication in general, is it's done over the airwaves. There's no additional wiring directly to the homes or businesses. You just plug the meter in, allow it to join the mesh, for instance, and then away you go. And like we said, the mesh networks have built in a great deal of redundancy for fault type conditions. And one other thing I wanted to touch on here is in the communication platforms in general in this type of field have become really stable and have even expanded their network capabilities to other devices other than just meters, of course, right? This allows the utilities not only to start talking to meters, but other devices, either that support the grid, support the communications back to the head end, but other devices that you could see, and if any of you've done any research on smart cities, or maybe you're deploying some type things, these are the kind of Internet of Things type of devices that can be used in cities, whether they're streetlight controllers or cameras, audio pickups, gunshot detectors, those types of things, traffic monitors. And they're all residing on these same radio networks, right? So not only can the systems and the utilities use these devices for their intended purposes, but if you're using a mesh network topology, they could actually be used to expand that the range of the mesh, right? So if you have an outlier from your main concentration of meters, perhaps you take a darkened highway and fill that highway up with or the back road or whatever up with the LED streetlights that use the network lighting controllers on top of them, and now you can get down that dark road down to that house that's out in a mile away from the city all by itself, and now you have a communication pathway through these devices that are mounted to the streetlight poles. Of course, the big the big issue with any AMI implementation and radio networks like this is to maximize the number of meters reached by the system, right? So of any of you guys that have already done your AMI rollouts, you know that that magic number is usually in the 95, 99+% read rate for your meters. You don't want to have to roll trucks out to some remote location all the time to get a meter read. Kind of defeats the purpose of that AMI financial justification. and you're trying to cut back on those manual reads as much as you can. We say here in the mesh network, they do use low power radio signals, that the planners and the designers for those networks have to keep all those things in mind, in order to make sure that they're reaching just about every meter in your territory. And it's imperative, from site to site, especially if you're installing new meters, to have the proper test equipment to kind of make sure that wherever you're putting your meter, you are you're making sure that it can join that mesh, right? So it's got to have a good signal strength. It's got to be away from noise sources, and the like. Typically, what you would use at a minimum would be a signal strength meter, like the one we have pictured here, 1120 from TESCO, and that's just it's a device that you can, your installers can take out with you. It's got an RF band on it. Typically what you can do there is just it's a general sense kind of meter, right? So you're going out there to see where you're picking up that radio frequency, right? And if you know the band that your particular network is working on, you can kind of look to see that it's in that correct band. So you're just looking for kind of a signal density type of location to either set the meter, or if you have a repeater for a certain area, you want to have a device like this to kind of be able to read that signal density in the area. One thing I would say here is this type of device is a good place to start, but it does become challenging when you're in an area where other devices and systems that really have nothing to do with the meter network exist, but they're residing in that same RF band, right? So one of the things that you can that the mesh networks in particular do, and this is a little bit of a difference why I talk about this device and the meters. The meters themselves are there is some redundancies built into these mesh network protocols where the RF interference that you might see from other devices can be mitigated by a technology called, it's either frequency hopping, is a term that's been used. I forget, there's another spread spectrum, I think, is another name for it. And basically what that means is the mesh will work in a particular band. So if it's having trouble at a certain frequency, it can hop between different frequencies within a certain band to be able to mitigate the problems with RF noise, or RF interference, I should say. But I believe, John Carroll, if you're on, I think you have an example of that for me, do you?
Yeah, hi. Can you hear me okay?
Yep, we're good.
Yeah, great presentation so far, John. Yeah, appreciate it. Yeah, my example was something I witnessed some years ago, and it is in a frequency domain, not quite with the RF side, but it was a very interesting application. The customer was in rural Oklahoma. They were doing fracking, which is the hydraulic pressure fracking that they use. And these are pretty crazy devices that they use. They're not in donkeys that we see sometimes on the side of the freeway there. And the problem they were having was they'd put in, the utility had installed AMI technology some years before, and this was 45, nearly 50 miles away from the headquarters, so it was quite a stretch for them. They were getting reads every day. They were polling them, and they only required a read once a day. But the customer decided to do an installation and an upgrade on their pump jacks. And they put in a fairly intense and substantial AC/DC drive panel, which was giving them more efficiency and reducing the cost for him. But like everything else, there are sometimes unintended consequences. So when we did this test, I was actually running a sort of customer load test on the site. The service panel was right beside this cabinet. and the meter was there, and they just simply couldn't get a read. So the difficulty they had is how to see what the read is. The only option was to go and physically read it twice a day, which was going to get expensive.
Yeah.
And the customer said, okay, fine, do it, because they couldn't shut down this thing. It takes 8 to 10 hours to reduce the pressure, which is 1500 psi. So it was a difficult one. But the bottom line was, to give you some idea about this, was we did a test with a meter, which we have with the 6330 meter, which is like a field service meter. This, I was guessing, was going to be something to do with harmonic frequencies, and it was. So these drives are called pulse width modulation drives. So they have a pulse that's constantly moving and adjusting, which is great. And it allows for multiple ranges on these different types of pumps. Typical pumps are a single stage. These were like 3-stage pumps. So there was a big efficiency saving in it. However, it was generating a significant amount of harmonic content. It was so close to the meter that it was basically interfering with it, and it was preventing the read. So we did some studies, we got some information. If I remember, it was in the kilohertz region. I can't remember the exact number. I'd like to say it was like 27 or 29 harmonic, which normally is insignificant. But in this case, that was the frequency that was interfering. And it was, excuse me, it was like an offbeat frequency, but nonetheless, it was a problem. So the ultimate end result was we shared that information. They went and talked with the customer. The customer talked with the installation team that put the drive system in, and they recognized that that possibly could be an interference. So they put in some filtering. They put in some low pass filtering to try and reduce that harmonic, and it reduced it enough so they could get a read from it remotely. So it's an unusual one, but it existed out there for sure. So these are things that we have to watch for with all of these hundreds of frequencies around everywhere. So
Okay.
that was the application.
Thanks, John. Appreciate that.
And John, right before the other John told his story, we had a question come in. What you were referring to before, I guess the meter is used for any network, or can it be specified for one network too? Does it identify the different band interference?
So I think we're talking about this one because I haven't gotten into the next one yet. So this particular device is just set to a certain frequency band, and it'll give you the amplitude for that band. Any signal falls into that band, right? So it doesn't discern from one network to the next, and it's not necessarily going to discern interference from it. It's not finite in its frequency measurement, right? So it's not tuned to a particular frequency. It's just in that band. And again, it's used as a kind of general tool. Typically, it's much more useful in areas where you're not going to get any other kind of RF interference, and you can kind of just look at the signal levels, assuming that the majority of the signal levels there are for the meter radio network. Another device that we're nearly complete in our development with is a Catalog 1160. We've got this out in the field, and we're deploying this up in Canada actually, to do some testing. This is kind of maybe the type of device that the last question came in on. This is a little more suited for that. This particular device is not just a general RF meter, right? This is actually kind of a meter in a box, if you will. So it's again battery powered, handheld. It's got a touchscreen on it. And what it has inside of it is actually a radio card, just like the ones you would put in a meter. And that radio card has been set up with an address. It knows what network it's on. It is secure in the sense that the utility themselves are actually going to program this device for the network that they're using, and all the security involved in that. So the utility folks are actually going to be walking around essentially with a powered meter in their hands. In addition to that, however, we've got our own circuit board in there and processor and software. And what it does, it goes out and it queries the network, right? So it goes out and just starts pinging and saying who's nearby, right? And then you'll see on the screen, it's a little bit of a hard shot that I put in here, but you'll see on that screen, you'll see the network IDs start to pop up on the screen. Right now, it only shows one, but you know it can show as many as there are available in the region where you're holding this device. And not only will it feed you back the ID numbers for each one of the meters, repeaters, collectors, whatever devices are on that network, but it'll also give you the signal strength ratio. It'll give you, in the case of the Landis and Gear, it'll give you the tickle percentage, data rates, all those different things that the you know, network engineers are looking for when you go out to do, you know, kind of a site survey for networking. So this is actually, you're going to walk around with this device and it's constantly querying that network, and it's constantly updating the display with neighbors, we'll call them, right? So, and you can, we can program this thing so that you can have qualified neighbors and unqualified neighbors, so that if you're picking up a certain device, but it's, you know, it'll show up on this screen, but it's got a fairly low signal to noise ratio, we can eliminate that from the screen, or maybe highlight the ones that are better neighbors than others. And then this way you can rest assured that wherever you're holding this device and you see, you know, a bunch of really good neighbors, you know, that's a great place to either place the meter itself, or if the meter position is kind of fixed by the installation type, you can take an antenna from the meter and place the antenna, like if you're in a basement or something like that, for instance, you can take an antenna from the meter and wire it out to a location that's that can be easily that's more kind of line of sight to other meters or network equipment that's out there, and be able to place it pretty accurately with this device, right? And right now we've got the units built for the Landis and Gear networks, but we can retrofit this and build it up for any of the other popular radio networks that are out there. Let's see, we're running out of time here. So again, a couple of things to keep in mind for if the meters are either too far remotely located, there's other impediments to getting that signal to or from the meter. There's a number of things that you could do, as we discussed. You know, a fair response to that would be looking into PLC communications. Again, the infrastructure and the wiring is already there. Of course, there's a fairly big price tag associated with applying the new you know, technology for the networking, the communications. And as I mentioned in the last slide, meters can actually have antennas connected to them and then mounted remote to the meter. Actually, John Greenwald, if you're on, I think we have a quick example of where we helped out a customer with antennas.
Yeah, can you hear me okay, John?
Yep, we're good.
Great, great. Yeah, so one of the large utilities local to us, they were having issues communicating with Elster meters that were in basements or installed in, you know, big metal enclosures or secure facilities, sub-level basements, you know, that sort of thing, especially in the downtown area. And the Elster meters had a board for external antennas. We worked with the utility to develop the process for installing those antennas. and creating the installation kits for the field. So it started with 25-foot long antennas, and then ended up going all the way to 300-foot long antennas with larger diameter cables, as the meters were getting further and further, deeper and deeper away. So, what we typically do when we do projects like this for utilities is, we'll work directly with the meter manufacturers and the installers to help minimize the utilities involvement to make it as easy as possible on a utility. So we'll receive, the meters from the manufacturer, perform all the acceptance and sample testing, do pre and post modification testing, which you got to do before you go modifying a meter, along with, developing the installation kits, and then, we'll stock those kits for the utility as well. And then, we'll manage the stock levels for, both the meters and the installation kits, and, work out a monthly report type of thing with the utility, advise them on when more meters need to be ordered, to keep stock levels up. But the key for us for at least for that particular project was we're the only vendor, at least that I'm aware of, who was approved by Elster to perform this retrofit where the original warranty on the meter stayed intact. So, that was the big deal about that whole project. Sorry, I had to throw that last little shameless plug in there. But yeah, we do that sort of thing all the time for utilities. Absolutely, as a service.
Great, thanks, John. Appreciate it. Okay. So a couple of the other things that I know we're running short on time here, I'll just touch base. Of course, some of the other things that are possible, we've heard everything. Of course, cellular is a big alternative that's becoming more and more popular for remote and hard to reach meters. Even Ethernet, and I heard one utility actually even talk about satellite phone communication from remote meters. As I mentioned earlier, of course, if you're considering AMI or you're in the middle of it, you know about these things. Trying to get that read rate, as high as possible and approaching 100%. We've heard stories from different utilities, especially in our user conferences, where they talk about all the different things that they are trying or would give their right arm for a method to reach that the remote meter, and as much as we can, as John mentioned, we're doing everything that we can to help you guys out with that. The one thing to keep in mind also is the more alternative types of communications that you use in that kind of deployment, you're either going to run into a problem with having to track different SKUs for particular meters and tracking them, figuring out who's going where, what stock you have, or if you just say, heck with it, we're just going to put all the communication modules in every meter, but then you're running up your cost on the meters, and chances are that the power level draws on the meters themselves with multiple communication modules in them also kind of goes up, which is cost burden to the utility. And then the other thing that I mentioned earlier, with that expansion of the different protocols into other devices, I talked about that example where you have that remote meter that's down a country road somewhere. You want to put up some LED streetlights there and put those NLCs on top of there. You kill two birds with one stone. You make the road a bit safer, and also you increase your pathway to getting that meter onto the network. Okay, I think we're out of time, Andy, but if there's any other questions that came in.
Yeah, certainly. We'll put a Q&A up. So thank you so much, John. And for anybody that was counting, we actually had 3 Johns giving some information there. So thank you to John Carroll. Thank you to John Greenwald. As always, you guys have any questions, you can also reach out to any of us directly. We will stay on a little longer. I know some of you might have to go. It's the top of the hour. We appreciate you for hanging on. And we'll keep the Q&A open on the chat if you guys want to put something on there. And there was a question that came in about will we have a field demonstration of the 1160 signal strength analyzer on our YouTube channel. So I know, we're working to get that done, and you're working with, I guess, one of the customers or something. So hopefully that will be happening in the near future. As we get our new products out, we try to, create videos and, get those out to you guys. So our YouTube channel is always a great place to go. And also on our website, you can always search for any of the products and things. If you have questions about them or you want to see a video about them, if we have it, it's all going to be up there. And as always, we'll post them online again, tescometering.com/Tesco-Tuesdays is all the information there. And our summer session, we will be, we're putting that together now, so we will bring that to you guys shortly. We're going to take a couple weeks off here, but we'll definitely be sending you guys that content and taking all your information from our survey we did. So thank you all who have participated in that. And finally, just a shameless plug on my part. It's our Tesco's users group in July in Philadelphia. Things are opening up, so we are having it in person. We talked about possibly virtual if somebody can't, attend in person. So we're looking into that in the back end, but we would love to have you guys in person. We'll have more of these kind of discussions, more in detail about our products, but definitely something worthwhile looking into. If you have any questions about that, it is on our website, or you can email me directly. And I think with that, I'm not really getting many questions on the chat, so I think we are good to go. So again, thank you guys. Thank you to the Johns today.
Yeah, thanks
And
you all
yeah.
for showing up here.
Yeah, we appreciate you guys sticking this session out with us. I know it was a long couple weeks for our winter spring. We are putting together everything for the summer session. We can't wait to see you guys again, and we'll get that out to you guys very shortly. So have a great rest of your week, guys, until we get back on TESCO Tuesdays here. Take care, everybody. Thank you.